Today's lecture will be talking about the greenhouse effect and global climate change, also called global warming. The purpose of the lecture today is not to convince you of my opinion or get you to believe what I think. It's also not to convince you of a specific opinion. I'm not trying to convince you that global climate change is something to worry about. I'm not trying to convince you that it's not something to worry about. We're just going to talk about the facts today, the things that we can prove with science. Before we can really discuss global warming, we need to talk about where does this energy that warms the planet come from. And we know that it comes from the sun. The sun warms us up. Since the sun is a black body, we need to review a couple of terms, namely what is a black body. So I think we've used this term before. Well, I know we've used black bodies before, that term, but there's a nickname for black body. Oftentimes we call it a perfect emitters. Black bodies are perfect emitters. And I think we've said that before in class. The definition of a black body, though, is something that never reflects any light. It does not reflect light. Instead, it always absorbs all incident light. Okay, so all light that comes off of it, all energy that comes off the sun was emitted by the light. It's a perfect emitter. None of it was bouncing off and came from somewhere else. The area under these graphs is considered the intensity. Intensity is a term you need to know. It is defined as the amount of power emitted per unit area. Okay, here's the equation. This equation is found in your IB data booklet. A good way to think about intensity is if you do something like take a flashlight and shine it on a piece of paper that's really close, that flashlight or that light will be really bright. If you take that piece of paper and you move it farther away, you'll notice that the paper doesn't look as bright. That's because it's the same power or the same energy coming from the light bulb, from the flashlight. It's just being spread out over a larger surface area. So therefore, it is not as intense or not as bright. So if we want to actually calculate the intensity of a light, like for example, we want to calculate the intensity of sunlight on the surface of the Earth, we first need to be able to calculate the power, right? Intensity is power per unit area. So before we can calculate intensity, we need to know the power. We've seen that the hotter something is, the more intense it will be. That's because the hotter something is, the more power it will emit. There is an equation to calculate how much power a black body radiates, okay? The equation is this. Radiated power emitted by a black body like the sun is equal to some constant called Stefan-Boltzmann's constant, which is right here. This constant can also be found in your data booklet, times the surface area of the black body, so the surface area of the sun, if that was what we were calculating, and then the temperature of that black body. So, and make sure you always measure that temperature in units of Kelvin. This equation is also found in your IB data booklet, okay, under topic 8. Keep in mind, though, that black bodies aren't the only thing that emit electromagnetic radiation. The sun gives off electromagnetic radiation from all spectra. So from all parts of the electromagnetic spectrum, that includes light, right? The sun gives off light, it gives off radio waves, it gives off ultraviolet, infrared, microwaves, x-rays, gamma rays, all these different wavelengths of light. It will give them all off, okay? However, other objects also emit electromagnetic radiation. I do, the Earth does, everything does, okay? It will emit energy in the form of electromagnetic radiation. However, if it's cold or relatively cool, like we are or like the Earth is, it will emit radiation in the infrared spectrum, which your eyes cannot see. So when we turn off the lights, I will be emitting electromagnetic radiation. However, you will not be able to see it because it's not visible light. It is infrared. So because of this, we give off energy as well, and so we can actually calculate how much energy we also give off with this same equation. Anything that's a non-black body will also give off energy with this equation. However, the energy is going to be slightly calculated slightly different because we are not a perfect emitter. We emit less. So to calculate how much we will emit less, what we do is we simply multiply this equation, this part right here, by a number to decrease the amount that the power is giving off. So we're going to multiply it by a number, E, we'll call it, and that number has to be less than 1. So E is called the emissivity, and it ranges between 1 and 0. If it's 1, that means it's a perfect emitter, or in other words, that it's a black body. That's why with a black body, the E just drops off. Okay, this equation will also be found in your yellow packet, your IB data booklet. It's kind of silly that they give you both of these equations, one with an E, one without an E. This one is meant for black bodies. This one is meant for everything else. However, you could still use this one. You just make the emissivity 1 when it's a black body. So it's kind of silly they give you both, but they do. Emissivity has a specific definition. It is defined as the ratio of the power emitted by an object to the power emitted from that, or the power that the object would have emitted if it was a black body, right? So it's the ratio of what it could have potentially emitted if it was a true perfect emitter versus how much it actually emits. So they calculate how much they theoretically should have emitted, and then they actually measure how much it does, and the ratio of those two is considered its emissivity. It's basically a percentage of how well it is emitting. So you can see from this graph, right, this might be the black body curve. So this is if it was a certain temperature, this is the shape of the intensity per wavelength, right? However, if it was not a perfect black body and it had an emissivity of 0.8, then everything just decreases. The whole thing just goes down and shrinks, and then it's smaller. This is not because it's a cooler temperature. It could still be the same temperature, but it's not emitting the way it should. It's not giving off the same amount that it should. Therefore, the emissivity is a little bit lower, and the graph just shrinks. Or if it's only 20%, the emissivity is only 20% or 0.2, then right, it shrinks even more, and it's the same shape. The peak doesn't shift over anything. It's the same exact shape, just smaller. Let's try a quick practice problem. If the sun has a radius of 6.96 times 10 to the 8th meters, which it actually does, and a temperature of 5,778 degrees Kelvin, then how much power does the sun radiate? Okay, in order to keep this, you can pause it and try and solve this, but to solve it, just keep in mind that we're going to use the same equation we actually did before, or we just discovered, right? Except that since the sun is pretty much a black body, we're going to plug in 1 for the emissivity, right? And that's just going to pretty much go away. Also keep in mind for the area, you're finding the area of the sun, and the sun is in the shape of a sphere. So you have to use the equation for the surface area of a sphere, which hopefully you remember. If you can't remember, it is 4 times pi times the radius squared. Okay, so go ahead and pause it and give it a try and see what you can calculate. Once you've done so, you will find that the surface area turns out to be 6.09 times 10 to the 18th square meters. And then when you take this surface area and you plug it into the equation, you will find that the answer should be 3.85 times 10 to the 26 watts. So that means that the sun is giving off 3.8 times 10 to the 26 joules every single second. That's a whole lot of energy. Okay, so what we usually care about is we care about how much is this energy hitting the Earth. So this energy, right, is being spread out. We've calculated the power, but we want to know the intensity of the light on the surface of the Earth. So this energy that we've calculated using this equation, right, the E is dropped because it's 1, we found that the power was this amount, and all that power, all that energy is going out, and it's not all going straight to the Earth. Not all of it is going to the Earth. It's actually spreading out in all directions. So it's going out everywhere. Only some of that is ending to the Earth. So if we want to know how much is hitting the Earth, we should calculate the intensity, right? So we can know the power per unit area because it's spreading out. So in order to do that, the trick is we need to get the power in the area. The power is easy. We've just did that. So we take this number, plug it in there for the power. The question is what do we do to find the area? Do we do the area of the Earth? No, we shouldn't. But that's because if we were doing the area of the Earth and we took all this power, that would be like we're saying all of this energy ends up on the surface area of the Earth. It doesn't. It goes everywhere along this area. So what we're doing is we're taking all this energy and we're spreading it around the area of this circle. Actually, it's not a circle. It's a giant sphere. Okay, so this sphere here, it's spreading out all along. And the intensity here, where the Earth is, should be the same as the intensity here, and the intensity here, and the intensity here. We're taking all that energy and we're spreading it out along the surface area of that sphere. So the surface area, this area here that we're going to plug in, should be the area of this sphere, which means we need the radius from here to here, or in other words, the distance from the sun to the Earth. Okay? the intensity on the surface of the Earth should be greater than the intensity on the surface of, let's say this is Mars. This is because even though the same amount of energy is being sent in all directions, the energy is being spread out along a larger surface area for Mars because it's farther away. This is just like when we shine a light, right, the flashlight onto a piece of paper when it's close versus far away, right? That light will spread out more when it gets to the area where Mars is. Okay, so the light will be less intense. So we're going to quickly calculate what is the, oh, sorry, I forgot this. So how do we calculate the area? Don't forget it's 4 pi r squared, and then the radius is just the distance from the sun to whatever planet. Okay, so if we want to quickly, we're going to quickly calculate the intensity of the light on the surface of the Earth and on the surface of Mars. So we can use this information. You can pause it and calculate. Once you do, you will find that the intensity on Earth, right, is going to be as follows. We take the same power, plug it in. We're going to use the radius, meaning the distance from the sun to the Earth, plug it in, do all our math, and we get 1,361 watts per square meter. That means that there is 1,361 joules of energy hitting the Earth every single second per square meter. So this isn't just this isn't the total energy hitting the Earth. This is how much energy is hitting the Earth every second for just a square meter worth of area, right? There's actually a lot more energy hitting the Earth because the Earth is very large. This is the intensity or area or power per unit area. Okay, so let's actually calculate then the answer for Mars. We get 579 watts per square meter, and we can see it's obviously smaller. Even though the radius isn't twice as big, the intensity is pretty much half the size, and that's because in the equation, right, 4 pi r squared, right, the radius has a big effect because this is area we're talking about. So light is coming in and hitting the Earth. Some of it is absorbed, that light energy, some of that energy is absorbed, and some of it is reflected because the Earth is not a black body, right? We've already looked at that. So that means that some is reflected out. Notice these arrows are thinner. That's because some is absorbed, some is reflected out. Now what this has to do with is a term called albedo. Albedo is the ratio of energy that is reflected versus the incident, okay? Or mathematically, that would be the albedo, or alpha, is the total energy that is reflected / scattered divided by the total power, right, or incident power. Okay, so we can figure out the albedo, okay, by just calculating the different amounts of, or the energy that is reflected versus the energy that comes in. However, there are different factors that affect the Earth's albedo. Okay, there is the season. For example, in winter, right, there's more snow and ice, and therefore the Earth will reflect more light than it will absorb. Okay, also other things might affect, like the temperature. Similarly, the temperature might affect the amount that the atmosphere will reflect because of at different temperatures it might behave differently. Also, cloud cover can also affect the Earth's albedo as well. White clouds are white, and white is when something is white, it will reflect all of the colors. That's what makes it look white. And so cloud cover, being white, will reflect more light. Okay, the Earth's actual mean albedo is about 0.3. That means it's about 30% of the incident radiation is reflected. 30% of whatever hits the Earth is sent back out. Okay, now you are given this equation for albedo on your yellow packet. You are not given this equation here, and you need to memorize it. Sorry about the box, it's off center, but you need to memorize that the albedo of the Earth is 0.3, or about 30%. It's just a good random fact. Okay, energy, once it hits the Earth and it's absorbed, so the other remaining 70% that hits the Earth is absorbed, where does that energy go? Well, it is absorbed, before it was absorbed, and it was in the form of wave energy, or in other words, electromagnetic radiation. After it's been absorbed, just like when you sit out in the sun and light hits you and you absorb the light, you warm up, right? So that energy turns into heat. Now that heat will rise the temperature of the Earth, and we can calculate the rise of temperature of the Earth with an equation. We've already seen this equation, right? The equation that relates change in temperature with heat. The equation was Q is equal to mc delta T. This equation is going to be very similar to Q is equal to mc delta T, but ever so slightly different. It's Q is equal to Q is equal to AC delta T instead of M. So you drop the M and replace it with A because you're not really going to heat up the entire Earth from the sun. The sun will give the Earth energy, but it will not heat it all the way down to the center of its core. Okay, it really only heats the surface. So we're going to use this equation, Q is equal to AC delta T, where A is the surface area of the Earth. Okay, and C is very similar to C in our Q is equal to mc delta T equation, is like specific heat, which is what C was before, but instead we call it surface heat capacity. Okay, and surface heat capacity is where, specific heat capacity with the Q is equal to mc delta T was the amount of heat used per unit, the amount of heat required to raise 1 degree of temperature for every unit of mass. Okay, that's what specific heat was. Surface heat is now going to be the amount of heat required to raise 1 degree of temperature per unit of area or per square meter. That's what surface heat capacity will be. Now they actually give you this equation on your IB data booklet. So it's basically Q is equal to mc delta T, but they put it in a little weird form, right? They write it in terms of the surface heat capacity, and you can still use it. Now, if the Earth absorbs energy, it will warm up. However, the Earth is always absorbing energy because the sun is always shining on it. So the Earth will continually absorb energy after energy after energy, which means technically the Earth should get hotter and hotter and hotter and hotter and never stop getting hotter. It'll forever get hotter, and eventually we will all become baked chickens. However, it doesn't do this. We know it doesn't do this. The Earth's temperature stays relatively constant. Sure, it fluctuates from season to season, but year to year it stays relatively constant. Okay, that's because heat, or the Earth absorbs energy, the Earth has to get rid of some of that energy in order to maintain the same temperature. Okay, so as the Earth absorbs energy in the form of electromagnetic radiation, right? The sun sends light to the Earth. So here's the sun, here's the Earth. Sun sends light to the Earth in the form of all the spectrums, right? It's in electromagnetic and infrared light, microwaves, and gamma rays and X-rays, and all those different rays, sends it to the Earth. The Earth absorbs it and then spits it back out. Remember, you do not need to be a black body to emit electromagnetic radiation. However, since the Earth is relatively cool, it's one of these down here, right? It's relatively cool. Then the amount of, the spectrum that it's emitting is in the infrared, okay? So as it absorbs energy in all the spectrums, it emits the energy specifically in the spectrum of infrared. Now this is going to be really important for what we're doing. So compared to the amount of energy absorbed, how much energy should it radiate back out if you want to stay at a constant temperature? The two should be the same if you do not want your overall temperature to increase. Now granted, it will absorb more than it spits out during the summer when it does get hotter, and during the winter it does spit out or radiate out more than it absorbs, and that's why it cools down. But overall, in general, as a general average, it should be the same if you're going to keep the average temperature the same. So here's a picture of what the graph, or what like the energy is doing if you had no atmosphere. So for example, Mars has no atmosphere. So if this was Mars, right, energy comes in. I believe the intensity was something like 580 or something watts per square meter. So as energy comes in, some of it is reflected out, right? You can calculate the amount that is reflected out by using the albedo. Remember, the albedo is the percentage that is reflected. So if you take that percentage and multiply it by the intensity, or in other words, alpha I, this would equal the amount of light that is reflected. Now, the other amount, some of it's reflected, some of it is received. So the other amount that's not reflected would be absorbed into the Earth. So the total amount being absorbed would be the original amount, I, minus whatever is reflected. So it would be the intensity minus the reflected amount, or alpha, or albedo, times I. Now, how much, therefore, should be emitted if it's going to remain at a constant temperature? So if it's going to remain at a constant temperature, it's got to spit out as much as it receives, right? So that means the amount radiated is also I minus alpha I. and that is kind of a quick way to look at how much energy, right, is coming in versus coming out, and the amount coming out should equal the amount coming in if it's going to stay at a constant temperature. However, the Earth stays or does have an atmosphere, so let's look and see what it looks like with an atmosphere. With an atmosphere, very similarly, energy comes in, some is reflected out, and then it spits back out. However, the atmosphere acts like a giant blanket that ends up taking some of that light and reflecting it back down. Okay, it absorbs it and spits it out back down, re-radiates it out. However, I don't want you guys to think that it will absorb the incoming light. Well, it does somewhat, but it shouldn't just absorb the incoming light and spit that back out. It only absorbs the stuff trying to escape. And the reason is because our atmosphere is made out of certain elements that will absorb specifically infrared light, but not other wavelengths. So the sun, which is way up here, right, and shining light down to the Earth, is shining, remember, light in all of its spectrums. So it's shining electromagnetic waves in the form of light, infrared, ultraviolet, radio waves, microwaves, right, all of these different ones. And so a lot of them are getting through because the atmosphere doesn't touch these other wavelengths. It only worries about infrared. That's the main one that it will affect. So the lights, because they're not all infrared from the sun, will come in, get to the Earth will absorb this light. Then it spits it back out in the form of infrared. Remember, because the Earth is kind of cool. So it spits it out in infrared, and because it's now infrared being spit out, the atmosphere will start to absorb some of that and re-radiate some of it back. Some of it gets spit out while some of it comes back. As a result, the Earth will be slightly warmer, well, actually quite a bit warmer, with the atmosphere than it is without. It will still be able to come to a constant temperature, so the total amount radiated outward should in the end equal the amount sent inward. However, the total amount kept inside the system should be higher than with the atmosphere than without. It's kind of like standing in the cold without a blanket, right? Eventually your body will come to a specific temperature and it'll stay at that temperature as your body tries to produce heat and you lose heat at the same rate. But you're going to be quite cold. Or standing in the cold with a blanket, and so you will also come to a certain temperature where heat will escape as quickly as you can produce the heat. However, it will be a much warmer temperature, right? The atmosphere acts as a blanket. This result, or this effect, is known as the greenhouse effect, okay, is what it's called. And we're going to learn exactly what that is. So here's another picture of what this might be happening. This is a cool Sankey diagram of what's happening, right? So the energy comes in from the Earth, right? Maybe 342 comes in from the Earth. So this is incoming solar radiation. They've representing as 342 watts per square meter. Coming in, some of it is reflected by clouds, right? Some of it is reflected off the surface of the Earth. This is all the reflected stuff because of the albedo, right? Some of it is even absorbed into the atmosphere because some of it's still infrared. But a lot of it still gets through and is absorbed by the surface. When it spits it back out, though, it spits it back out in the form of infrared. So it spits it out, okay, and it spits it out towards the Earth. However, a lot of it's radiated back down. And so there's a bunch just bouncing around in here. In the end, though, the same amount that comes in will be the same amount total that leaves. Okay, the greenhouse effect, if we were to summarize it and we were to explain it, these would be the key summary points that you should keep in your notes. So, the greenhouse effect is the warming of the Earth caused by the following. So, radiation from all spectrums enter the atmosphere and is absorbed by the Earth. So it'll get through that atmosphere and it'll be absorbed by the Earth. Then the Earth re-emits that radiation or that energy in the form of infrared. Then infrared specifically will be absorbed by certain gases in the atmosphere, and then those gases will then re-emit that energy out or re-radiate it out, some of it back towards the Earth and some of it out. But as a result, it keeps that energy inside the Earth system and keeps it warmer. So this is an example or an explanation of the greenhouse effect, which you should be able to explain on a test. So there are different compounds that act as greenhouse gases, and and absorb this infrared radiation and radiate it back. One of them is water vapor. Carbon dioxide is one, and one of the ones that we are most familiar with. Methane gas is also one. Nitrous oxide and ozone are also some as well. So the reason why these gases absorb certain wavelengths, specifically infrared type wavelengths, but not others, is because molecules can act like masses on springs. If you'll remember right from our simple harmonic motion unit, when we took a mass on a spring and we let it wiggle, that mass liked to wiggle at a very specific frequency. In other words, it had a very specific natural frequency that it would vibrate at. Well, molecules kind of behave like masses on springs. For example, if you had O2, which are two oxygen atoms, those two oxygen atoms are bonded together. So it's like this, here's an oxygen atom, here's an oxygen atom, and they are attached to a spring, and they're just going to wiggle back and forth. The more energy they have, the more they wiggle. And they also have certain natural frequencies that they will respond to. According to which frequencies they like or that they will respond to determines which wavelengths or which frequencies of electromagnetic radiation they'll actually absorb. If the two match, it'll be able to absorb it. If not, it won't. Kind of like, when you push the kid on a swing at the right frequency, the kid swung higher and higher. If you push it at the wrong frequency, the kid wouldn't. This is a factor known as resonance. Okay, so similarly, the molecules will resonate with certain frequencies but not with others. Okay, the graphs here actually demonstrate this idea that certain gases or compounds will absorb certain wavelengths or frequencies of this electromagnetic radiation, but not others. This graph you should be familiar with. You don't need to memorize it, but the concept of what this graph is saying should be familiar. This is actually lots of graphs. Here's one graph, here's another graph, here's another graph. Okay, so the graphs are the x-axis are the wavelengths, okay, which can be related to the frequency. So the wavelengths of the electromagnetic spectrum, most of these shown here are all in the infrared. Okay, and then this y-axis is the absorptivity, or in other words, when it's high at 1, it's absorbing 100%. If it's low at 0, it's not absorbing any of it. So for example, if we come up here, methane, at this wavelength over here, it's not really absorbing anything, neither this wavelength here, or this wavelength, or this wavelength, or any of these wavelengths, up until this point, where all of a sudden, at this particular wavelength, whatever that is, all of a sudden spikes way up, and that's because it'll absorb that particular wavelength. That is one of its natural frequencies, and it'll respond, okay? It also kind of absorbs these, not really, but then it really absorbs this one as well, okay? So then we see on the nitrous oxide, very similar pattern, like little tiny spikes here, and then a big spike here, and then nothing, and then a big spike, right? And so, it'll absorb some frequencies, but not others. Oxygen, right, has a big swath over here. So there's actually quite a few that oxygen and ozone will absorb, and then a couple of little spikes. Carbon dioxide, you'll notice these are some pretty wide peaks, and there's another little swath over here. So there are quite a bit of different wavelengths carbon dioxide will absorb. The biggest factor is probably water vapor, right? Look at the width of all these different wavelengths it can absorb. It can absorb a lot of different wavelengths, and when they absorb it, right, they spit it back out and radiate back down towards the Earth. So this last one would be all of them added together, and you can see you've covered quite a few of the infrared spectrum. Now a very similar graph, but that is backwards, and I've also seen this kind of graph just appear on the test, and you just need to be familiar with both of them, right? So instead of showing you the wavelength and absorptivity, it's showing you wavelength and transmittance. So it's exactly backwards. So instead of each spike representing how much, or that it will actually absorb that energy, each spike is showing what it will allow to transmit through without absorbing, right? So these are just the ones that it will allow through and not the ones that it absorbs. Absorbing would be the ones that have zero transmittance. So this particular wavelength, right, water vapor absorbs quite well. Okay, let's find a particular spike, right? CO2 and nitrous oxide, right? There's a spike right here that shows that it will absorb it because of these two gases, right? So this is a transmittance one instead of absorptivity. You could see a graph with either one. Okay, so we have learned how to calculate the power coming off, or the energy coming off of the sun. We've learned how to calculate the intensity of sunlight on the surface of the Earth by the time it gets out that far. And we have learned the equation as shown here that will allow us to take that energy and figure out how much heat or how much the surface of the Earth will increase its temperature. However, this does not have intensity in it. So how do we get to intensity to actually changing temperature? And it's easy to do, but we just got to do a little bit of math. And they actually, since you're going to do the same math every time, they've actually derived a new equation for temperature change in terms of intensity. So I'm going to just quickly derive that real fast. Okay, so the following, we're just going to rearrange this original equation so that we're solving for change in temperature, and we get this. We're going to rearrange this equation by doing algebra. Right, Q over AC is the same as Q over A times 1 over C. Okay, so it's just algebraically, this is the same thing. And now we will make note that intensity is power per unit area. Remember, power is change in energy or work per unit time. So intensity is also equal to energy divided by time times area. Okay, so over here, that's similar to heat over area, except this is, because heat is energy, right? So this is energy over area, and time is on the bottom. This is just energy over area. So we got to get time in the equation so we can get intensity in here as well. So what we're going to do is we are going to divide by time, the whole equation by time, so that time is now down here. And we're also going to multiply by time, so time is on top. So that way we don't have to worry about, or so that way we haven't actually changed the equation at all. When you multiply by a number and divide by a number, it's not going to change anything overall. Now we can take all this stuff right here and we can replace intensity in there. However, since this right here, since heat is actually the change in energy, right, not just energy, this will actually be the change in intensity. So we plug that in here and we get change in intensity is equal to change in time divided by CS. And that equals our change in temperature. Or we can rearrange and we finally get the equation. Change in temperature is equal to your change in intensity written out this way. So it's, in other words, your intensity in, meaning the stuff you absorb, minus intensity out, meaning the stuff you emit out, right? So that's how much your change in intensity would be, because you're absorbing some and then you're spitting it back out, right? So change in temperature is equal to intensity in minus intensity out, all times the amount of time, how long it's been absorbing for, divided by CS, which is, again, the surface heat capacity. This equation is also found in your IB data booklet. You just need to know what the variables are, what they represent, and what to do with them, and how to calculate it. So just a quick check-in. What happens when the amount of energy that leaves the Earth is slightly less than the amount that is incident on the Earth? The answer, it'll warm up, right? So you're absorbing more than you're spitting back out, and it'll warm up. So when intensity in is greater than intensity out, the Earth is going to get warmer. When can this happen? Because remember, we want the Earth to stay at a relatively constant temperature. Well, this does happen. This happens on a seasonal basis. Every time it hits summer, the intensity in is greater than the intensity out, and the Earth warms up. Then it hits winter, and the intensity out is greater than the intensity in. So it's emitting more than it's receiving. And so then the Earth cools off. Right? So this actually does happen very often every year. Okay. On average, though, we want the two to be the same, so the temperature of the Earth stays relatively constant. However, it's not necessarily going to be the same. We will still gain heat or lose heat, or we have been as a large trend, and that's what we're talking about, and that's what we're calling global climate change. So global warming or global climate change is just this idea that temperature as a whole is actually not just changing by the seasons, but it's changing and increasing over time. Right? So if you take the average temperature of the Earth and you plot it every year, right, you will get a graph that looks something like this, right, where the temperature goes up and up. Now, keep in mind, we're scientists, we're not politicians, we don't just interpret graphs the way we want and manipulate things. So don't forget on all of these graphs, because a lot of these may have been these graphs that we have gotten that are in books or on the internet or wherever you might find them. Okay, a lot of them you will find will be posted by someone who has an agenda, someone who's trying to convince people of stuff, right? So oftentimes they will manipulate the graphs. Keep in mind, so this graph right here, look at the graph, look at the axes of the graph and make sure you understand. So this is over 130 years of time, and you'll notice that the temperature does rise, and that is true. It has been rising, but notice the temperature difference, right? 0 is supposed to be the temperature that you would expect the Earth to be at. So at first it was colder than what we normally expect the Earth to be at, and then it warmed up more and more and more and more, and the actual temperature changes from negative 0.2 up to, I don't know, negative 0.5 or something. So that's a change in temperature of about 0.7 degrees. That's not very much, right? But it is a change in temperature, and actually a little bit of change actually does cause a difference, and it makes a difference. However, just keep in mind that this looks like a huge increase. It's just 0.7, so always make sure you look at your axes. Now, the average temperatures are currently close to an all-time high for the last 400,000 years. Okay, so we're going to look at how do we even know that? How do we even know the temperature? In fact, at this time we want to discuss what are the possible sources or reasons why this temperature might increase. Okay, so if you want, you can pause and try and guess. Here are some of my ideas of what, and other scientists' ideas of what might be causing this. Okay, one of them, of course, is the most commonly accepted one from a lot of scientists, and that is that the changes in the composition of the greenhouse gases in the atmosphere could be affecting this. So in other words, if we get more greenhouse gases, we'll hold in more energy, and therefore it'll warm up, right? So also other ideas could be that there is an increase in solar flare activity, which is true. It has been increasing. A solar flare is basically like a giant explosion on the surface of the sun, which spews stuff out in the air, or sorry, not out in the air, but out away from the sun. It does come back in, but at the same time, it increases the solar radiation. So it gives it a burst of energy, or shoots out a burst of energy from the sun all at once, and so that means that the actual energy coming off the sun is ever so slightly higher than what it would normally be if there weren't as many solar flares. So it could be that's the reason why the temperature is increasing. It could also be the fact that the Earth's orbit is changing ever so slightly, right? If we ever get a little bit closer to the Earth, if the Earth ever gets a little bit closer to the sun, then that means our intensity will go down because we're getting energy when we're closer, and it'll be a smaller surface area. Okay. Also, it could be even volcanic activity. Right? The Earth also has an internal temperature, and it's really warm in the inside, and so it could warm up the outside by having a lot of volcanic activity and bringing some of that internal heat out. And that is true that we have had an increase in volcanic activity recently. So which one of these reasons is probably accepted by many scientists? And the one that we're going to be focusing on today is the top one, the idea that perhaps it's increasing because the changes in composition of greenhouse gases in the atmosphere. That's the one we're going to be focusing on, but it could be other ones of these, and other scientists will argue one or the other. Okay, so it's not necessarily, we don't know for sure it's this top one, but a lot of scientists believe it's that one. There better be a reason for us believing it, right? Again, we're not politicians. We don't just pick whichever one we like and we go with that. We're going to pick the one that we have the most reason to believe. So there should be some evidence for us to believe this. So what are some of these reasons why some scientists believe an increase in greenhouse gases is causing the temperature to rise? Well, in order to really know, we actually have to look back in time. We actually have to look and see a trend, and that means that we need to see the percentage of greenhouse gases and compare it to the temperature over a long period of time. It's hard to do that. One of the ways we do that is by looking at ice cores. So what they did is they go to Antarctica and they drill down and they get out this core of ice. So they drill down with this drill and they pull out this core of ice like this girl is holding right here. And this core of ice, similar to a tree, which has different rings around it, has different levels or layers of ice. So just like a tree, right, you can look back hundreds of years, many years in a tree by the rings, and you can see, like, you can tell if there was a drought one year because the ring might be really thin, or if there's a black ring, maybe there was a forest fire one year. And it's kind of like looking back in time by looking at the rings. Similarly, snow falls every year and freezes, right? And when it falls, it gathers information about the atmosphere because it's passing through the atmosphere and gathers some of those chemicals or whatever's in the atmosphere at that time. So if you drill down through the ice, it's like drilling back in time, all these different layers from past years and hundreds of thousands of years ago, And you can look at all of these different layers, and you can gather information, and you can learn what the gas concentration was during those years. They have done this for hundreds and thousands of years to get the information, and you'll find that information in the following graph. This graph here is an example of the CO2 concentrations found in the atmosphere. Again, don't forget to look at the axes. Notice that this is a skewed graph. It doesn't actually go down to zero like it should. So this looks like it's like the concentration of CO2 is actually almost zero at this point. It's not. They're just trying to make the difference more extreme, okay, by zooming up. Keep in mind that this graph is actually longer and the extremes aren't quite as much, but it's still going up and down. And so from the beginning of time, so 400,000 years ago on the Earth is how far back they're looking at this. Okay, and they've noticed that at different times the CO2 level is really high, and then it goes down, and then it goes up, and then it goes down. And the Earth actually has a natural fluctuation of carbon dioxide. So there are natural causes for why carbon dioxide might increase and decrease and increase and decrease. Okay, this is even before where humans are on the Earth, right? So there's got to be some kind of natural reason for this. As we zoom up on the last 8,000 years or so, though, you'll notice an interesting trend. It stays relatively constant, and if you zoomed up on any part of the other graph, right, even though it went up and down and up and down, this is over hundreds of thousands of years, right? So these changes aren't actually that quick. They're kind of subtle. So when we zoom in, we should see even more subtle changes. Like this is a slow increase, right? A subtle change. But you can see right around the Industrial Revolution, boop, it jumps right up. Okay, and this is around the time when we were building devices that burn fossil fuels. So if we zoom up one more time, just in the last 50 years, right, you can see it go up and up and up even more. This is a very large spike for just 50 years. That's a very, very fast spike, which is very unusual for the rest of the time. Okay, it usually never jumps up quite that fast. You can see similar trends with methane gas. Okay, and again, near the end, you see this giant spike of methane gas. Again, zooming up. Okay, however, why does this mean that this might be causing temperature change? Just because there's fluctuations in CO2, that doesn't necessarily, or other greenhouse gases, that doesn't necessarily guarantee that that's the thing causing a temperature change. So why would we think that it's causing a temperature change? Well, the reason is because we look at when you look at two graphs at the same time, you start to see an interesting trend. So up above is the CO2 graph, right? It goes up and down. This is the one we've already seen. And then down below is the temperature one. And if you look, there's a very interesting correlation. Each time the CO2 is high, the temperature is high. Each time the CO2 is down, the temperature is down, right? Sometimes one falls before the other, right? They're not perfect correlations together, but there is a large correlation in general, a large general correlation. So every time spike, spike, low spike, low spike, 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 right? Spikes, two spikes, and then two spikes, right? And then it goes down, and then this goes down. And there is a large correlation between the temperature and the CO2 levels. So that's interesting. We can't prove that that's what's causing it. This isn't proof. But what this is this is showing a large correlation. And so it makes us worry that when one goes up, that means the other one's going up. And since at the last couple of years, we have seen this giant spike on the CO2, right? Remember, in the last couple of years, we've seen this giant spike. Then we're worried that the temperature, right, will also spike. That's the worry. Will it? Oh, I don't know, but we're worried that it will. So as we see this giant spike, that's what we become worried about. Now the next question is, what is causing that CO2 to spike? So there could be different reasons to explain why these other CO2 and other greenhouse gases are increasing. The most common belief is simply that we're burning a lot of fossil fuels. And probably the reason why we're believing this the most is because, again, remember that spike just happened to start right around the Industrial Revolution. And so it's rather coincidental, I think, to have this giant spike right at the time when you're burning a lot of fossil fuels, which we already know give off a lot of CO2 and other greenhouse gases. So it is rather, I mean, it's kind of just the simplest explanation of what might be happening, since it just happens to correlate around that time. However, it's not the only one. So other possible causes for the increase in greenhouse gases include the following. Number one, there could be increased volcanic activity. The Earth stores a lot of CO2. Excuse me, the Earth stores a lot of CO2, and during volcanic activity brings a lot of that CO2 out of the ground and into the air. Also, an increase in forest fires. Naturally, forest fires occur all the time because of lightning strikes and things like that. However, with humans, right, we end up creating occasionally more forest fires than we intend. And so, or that more forest fires than if it was just nature, I meant. And so forest fires, in addition to causing deforestation when the forests are, the trees are trying to get rid of some of that CO2, the forest fires themselves is burning a lot of biofuel, which creates a lot of CO2 as well, kind of like burning fossil fuels. There are other natural processes as well. I mean, there's other things like just the fact that we have greater population, right? We all exhale and we all breathe out CO2. In addition to that, we all require food. So we have more cattle on the earth now. We have more people on the earth now today than probably the first 5,000 years of the human race, all put together. If you added everybody who lived in the first 5,000 years of the human race, we have more people on the earth now than we did back then. So there's a lot of more people. Now, in addition to needing more food, we also, and more cattle, we also need more space, which means more deforestation and things like that. Okay, in addition to this problem, we're also worried about some things that will accelerate the problem. So though the amount of increase in temperature for the last 130 years is only about 0.7 degrees of Celsius, that's not a huge change, but it's large compared to some other changes we've seen. But it's not that big. So the question is why are we so worried? Well, one of the things we're worried about is that as it warms up, things will kick in, processes will kick in that will actually accelerate the warming process. For example, as the earth warms, the ice melts, right? And remember, ice helps provide the albedo. The more ice there is, it's white, right? And it'll reflect, the earth will then reflect more. So by warming up and melting some ice, you lower your albedo, which means you're absorbing more energy, which means you'll melt even more ice at a faster rate, right? And so it just, one thing causes another and speeds up the process. Okay, other things is that there is more evaporation of water. And remember, water vapor was one of those greenhouse gases, right? So the hotter it is, the quicker the rate the water will evaporate, which means we get even more water vapor, which means we'll warm up even faster. Other things also include, right, that the temperature decreases the solubility of CO2 in the sea. Just like the earth, the water actually holds a lot of CO2. Okay, it just holds it in the water. And things like phytoplankton will absorb that and use that for photosynthesis and create oxygen as well, similar to other plants. So while the sea holds a lot of that CO2, as the temperature increases, it can't hold as much. The solubility of CO2 goes down, so it can't hold as much, and so therefore it has to release it. So increasing the temperature might release more CO2 from the water, which would just cause more of a problem, and if it really is the CO2 that's causing it to warm up, right? And then it would cause more of a problem, and it would just get faster and faster, warm up quicker and quicker. Some kind of doomsday scenarios of what might happen are as follows, and you should be aware of some of these scenarios. So number one, the average temperature they've modeled that it might raise by 2 to 4 degrees by the end of the next century. So in other words, in about another 100 years or so, it'll increase 2 to 4 degrees. Now notice, in the last 130 years, it only increased about 0.7 degrees Celsius. So the only reason why they might think it might increase another 2 to 4 degrees is because of these accelerating factors. So it's really hard to predict everything that's going to happen because the Earth is a very complex system. So keep in mind that all of these are guesses and predictions, and by using models of things we do know, but we may not have included everything that could happen, right? So a lot of these are our guesses. Other problems might also include having the sea levels rise, and they could only rise about or they could raise up to 20 to 60 centimeters. Now, that's actually not a whole lot of height to raise your water. However, you don't need a whole lot of height to cause some serious problems. Number one, a lot of our major cities in the world are all found really close to water, okay, and really on flat spots too. So even just raising 20 centimeters would cause a lot of this water, these cities, to be underwater. Now, when I say underwater, I don't mean skyscrapers underwater. I mean there's like a thin, 2 inches of water everywhere. Now, the problem with that is I don't care where you are. You cannot live when there's like 2 inches of water everywhere. Okay, you can't live in a lake where there's 2 inches of water. That water will cause damage in your homes. You won't be able to live there. It'll cause mold. It'll cause, malaria because mosquitoes will come in and breed and etc. And it just causes problems. You can't live on water. I don't care how big it is. You still can't live on it. So that would cause massive problems where people have to move and entire cities are basically destroyed just by a little bit of water. Other problems are severe storms. Storms are caused by the rapid change of temperature from hot to cold or cold to hot. This is why there's more storms in fall and winter than in summer and sorry, I said fall and winter. I meant fall and spring rather than summer and winter. So right as these temperatures change, it will cause more severe storms. Also, we could even enter a new ice age. The reason is because as the ice caps melt and some of that cold water goes into the ocean, we have water currents that go from warm places in the water to cold places in the water. And what that does is it actually acts as a conveyor belt of heat. It takes warm water, right, and moves it up to cold areas and actually keeps cold areas slightly warmer than what it should be without these currents. And if the ice melts, right, it'll cool down some water in certain areas, and it would basically disrupt these currents, and it could theoretically shut down the currents. And if the currents shut down, what that means is heat will stop flowing up to the top, and so near the top of the earth where it's cold will become even more cold, right? So while the earth is heating up as a whole, right, so the equator is getting hot, the top, if it shuts down these currents, could actually make it really, really cold, and so the ice would start to then cover a lot more of the earth. And it would just be the polar ice caps would just be huge instead. So this is another possibility of what could happen on long terms. Also, water can be more acidic, which can kill life. You can destroy ecosystems. There have been recorded incidences where, for example, I can't remember the name of the bird. I need to look it up. There's a type of bird that is endangered. It's because it usually feeds off of a certain insect, and these insects usually hatch at a very specific time. However, because the Earth has increased just a little bit in temperature, so again, last 100 so years, temperature has just increased 0.7 degrees on average, right? However, as it increases just a little bit, these certain insects that the birds feed off of always hatch at a certain time of the year because it's always a certain temperature, and now they're hatching just 2 weeks early. That's it, just 2 weeks early. And as a result, these insects hatch, they breed, they die, and then the birds come in to feed, but the insects have already hatched and are gone. So then they're in trouble, and it can disrupt different ecosystems, and we're even seeing that now. So there are too many factors to really accurately predict. Keep in mind that these are just scenarios, possible outcomes that we're guessing and trying to model with the physics and science that we do know. Okay, we talked about the sea level rising, and there's one thing that you need to know that's important is that it's not because of melting icebergs that will cause the sea level to rise. For example, in this picture right here, we have ice in a cup. The water is at the very tippy top. If this ice melts, water will not overflow. And the reason is because when water freezes, it expands, right? So as it melts, it will take up less space, and it'll all fit in the glass in the end. This water is already floating, this ice is already floating. It's not going to raise the water level. However, the ice that will raise the water level is ice found on land. So here's a picture of Greenland, right? And all this ice that's on the land, that's the stuff that we have to worry about. And you can see there's the ice in 1992. Here's the ice in 2002. And it is definitely a heck of a lot less ice. So water, this ice is melting and then going into the river or into the ocean. So keep in mind, melting floating ice does not change sea level. Keep in mind that it's only the stuff on land. Also, other things you should know is that as the temperature gets bigger, the other reason why the water level will be higher will actually be because the water in general will just simply expand. Anything that gets warm will expand. Here's a picture of a railroad track that on a very, very hot day where it has expanded to the point where it has just basically warped and just destroyed this train track. Okay, nowadays they actually put gaps in the train tracks so that there's room for the tracks to expand and then contract throughout different temperatures. So all things expand when they get hot, including water. Here's an equation you could use. You do not need this. I haven't ever seen an equation or anybody use this equation, but you at least need to know the general idea that the water does expand, and that's one of the other reasons why water level will increase. So what are some solutions? What could we do to help solve the problem? So there are different things we can do. Number one, there's different technological solutions we could use. Number one, we can make more efficient use of power, right? So anytime we use power, we could make devices that use it more efficiently. So more efficient, high efficiency washing machines and high efficiency laundry machines and high efficiency refrigerators, and you bet anything that will use less energy, because we have to often create that energy, often using fossil fuels, right? So by using less energy, we're burning less fossil fuels. Other things we could do is we could try and decarbonize exhaust, like from cars and stuff. That means somehow capture that exhaust and by some chemical process just capture the CO2 in the exhaust and store it somewhere, right? I'm not exactly sure how that would work, but you could do something like that. That's one of the things they're trying to look into. Also, other things is instead of just trying to solve it with technology, you can just try and reduce the energy requirements that you have, right? So kind of like more efficient instruments. You can try and do things like don't waste the energy as much, or by thermally insulating your home more, right? That way you'll require less energy. You can reduce the amount of travel you do, or somehow use more efficient modes of transportation. Take the bus, right? So more people are taking this or going on the bus, and so there's less gas burnt. You could use also systems that combine heating and power, right? So an example of that would be solar heating, right? So and you can also use it to make electricity as well. Things that combine both systems in one, you save some energy. And then the last couple of things would be to replace coal and oil sources of energy with renewable energy sources that don't create CO2. And you can plant a couple of trees, right, which would also help and a little bit to reduce CO2. Some of the worldwide efforts I don't know anything about.